angular speed, omega, when the block hits the ground. And to hit the ground, it has to move down 0.5 meters. Okay. So, as you look at this, probably think like, this is weird. Okay? When you encounter weird problems and you don't have a clear idea how to get started, how do you engage the problem? Draw forces. I mean, just start drawing forces. That is the lowest level of engagement. That's where you can always start. So when you start drawing forces, we have the mass hanging times gravity pulling down. We have a tension going up. We have a tension on the disc going down. We have a support force holding this disc in place. And we have the weight of the disc.
Mr. Cox.
Yes?
Let's say a question like this was on an AP test. Would we have to draw both tensions, or could we only do one since it's the same thing?
It's the same thing, but the two tensions act on two different objects. Okay? Now, after you've drawn a free body diagram for the disc, a free body diagram for the hanging mass, what's your next step? Sum your forces. I'm going to start with the thing I'm most familiar with, and that's the block. Okay? If I was summing forces for the hanging block in the y direction, I would have the tension going up. I would have the hanging mass going down. And anytime you sum forces, what is it equal to? MA. Ah, the first class all day, not to fail. Oh, never mind. I gave you too much credit. All right. But at least you recalled from yesterday, so kudos to it. Okay. So now, after we write the sum of the force equation, next step. Sum of the torques. You could try summing the forces for the pulley. It's not going to get you anywhere. Okay? The next thing that leads you to a productive place is summing torques. And when you look at the three forces that act on the pulley, what one force creates a torque? The tension. It makes the pulley want to rotate. So I have the tension, and to get a torque is force times distance. So I have the tension times the distance r, and they're perpendicular to each other, as they should be. And that's the only thing that creates a torque. And whenever you sum torques, what does it equal? The moment of inertia times the what? Angular acceleration. Or simply I alpha. When you sum forces, it equals MA. When you sum torques, it equals I alpha. Okay? We were told in the problem to treat this as a uniform disk. What is the moment of inertia for a uniform disk? 1/2 mr squared. So all that stuff is I, and I still got alpha here. Now if you look at these two equations, here's what I see. I see 1, 2, 3 different unknowns. The tension, the linear acceleration, and the angular acceleration. 2 equations, 3 unknowns. That's a bad day in math. Okay, we need something else. Okay, is there a relationship between the linear acceleration of that box going down and the angular acceleration of that disk.
Linear acceleration equals R alpha.
What?
Linear acceleration equals R alpha.
The linear acceleration, A equals R alpha. You know, in this formula, that A stands for the tangential acceleration of the disk. But the point at the edge of the disk, that's where the rope is. And the rope's moving as fast as the edge of the disk moves. So I can use A equals R alpha. And I can replace alpha with A over R. And when I make that replacement, this R cancels the square, that R cancels that R, and while everything is said and done, we get the tension equals 1/2 the mass of the disk times the acceleration A. Okay? Now, if I bring this equation down and I make this substitution into there, 1/2 the mass of the disk times A minus the mass hanging times gravity equals negative mH times A. Okay, rearrange some stuff here. And we can get our A's all together. Now, we're not really supposed to be solving for A, but A is going to help us find a lot of this other stuff. And if I was solving for A, I could factor A out. And last step, I get this. I think this is where we ended the period yesterday. And I said if you stare at that, you might see something. Anyone see anything? What? It's kind of like a systems approach. If the disk was massless, what would the acceleration be? If they had a string wrapped around a massless disk, it'd be gravity, right? Because if that was massless, that term wouldn't be there, and the acceleration should be g. Now, so the fact that you have to rotate this disk slows down the acceleration. But do you have the whole? But do you have to rotate, or do you have to move all the mass? Or you?
Half the mass, which is the outer.
It's only half the mass, which is what?
The outer part, where the radius is. No.
Nah.
It's like the average, because we use half because it's like a disk, and then if you've got the stuff on one side and the stuff on the inside,
That half.
It's hard to describe, but that half appears somewhere else.
Moment of inertia.
Notice that half is the moment of inertia coefficient. Guys, if I had a big solid ball and I drilled a hole through a ball and I wrapped a string around the ball,
2/5.
that half would be 2/5. Yeah. Okay. Anyway, let's finish the problem. So we can get a value for A. The mass hanging was 100 grams or 0.1 kilograms. G is 10 meters per second squared over 1/2 the mass of the disc, 0.8 kilograms, plus the mass hanging, 0.1 kilograms, A is what? What is it?
2.
2? Two meters per second squared. Now that I got that linear acceleration, can I start working on some of these things I need to find? Yeah, they're going to be pretty easy. Like, for instance, I got T sitting right here. T is 1/2 the mass of the disc times A. 1/2 the mass of the disc was 0.8 kilograms, and A was 2 meters per second squared. 1/2 of 2 is 1. 1 times 0.8. The tension is 0.8 what? Newtons. Check, got that one. What's the angular acceleration? Can I get that?
Yeah, just divide the potential acceleration.
A equals R alpha. A over R is alpha. The acceleration we just got, 2 meters per second squared. R, 0.1 meters. Alpha is what? 20 radians per second squared. Omega when it hits the ground. Okay, we got the two pieces of low-hanging fruit. This one's going to require a little bit more thought. Energy. You know what? Energy would be a fine approach, but we're not there yet. Okay? After we take our next test, I would go with energy. Right now, I would say it would be really easy to know omega if I knew what. Let me frame the question a little better. When that box makes it to the ground, if I could tell you the linear speed that it hit the ground with, could you give me the angular speed of the pulley?
Yes.
Anyone know how? Is there a simple relationship there? What? Someone's mumbling it. B equals R omega. That's right, Junaid. The linear speed of this thing, when it hits the ground, is tied to a string. That string is going to make the outer edge of this pulley move at that same speed. Okay? So now the question becomes, could I find the speed it hits the ground with? I think so. We've got an acceleration, 2 meters per second squared. We know it follows a distance of 0.5 meters. And we're going to assume that it starts from rest. Is there a way to get V final given that collection of stuff? Yes. What equation? V squared equals V naught squared plus 2AD. The initial velocity goes away. The final velocity is the square root of 2AD. The acceleration, 2 meters per second squared. The displacement is what? 0.5 meters. the velocity is, when it hits the ground, is
1.41 meters per second.
1.41. If you have a little brother or sister, and they take AP Physics, and they come home and they say, you know what that crazy Mr. Cox said? They said, everyone learns their kinematic equations. It's just a question of how many points they lose before they learn them. What are you going to say? Learn them earlier. Because he's right. They never go away. They take a sabbatical here and there, but they never fully go away. Okay? Once we have the velocity, we can get omega. V over R is omega. 1.41 meters per second. The radius, 0.1 meters. And you get 14 radians per second. Good? Okay? Well, let's look at the next one. Here we go. 100 gram mass is used to pull a 500 gram cart across the table. As shown in the diagram below. The cart may be assumed to be free moving and it has lightweight wheels. First question is, assuming the pulley is massless and frictionless, find the acceleration of the system. Have we worked this problem before? Okay? Yeah, way back when. Anyone remember the quick and easy way to do this?
Force opposing.
What? Treat it as a system. Okay? Now, to understand it, we might first want to start with a little quick free body diagram. I'm calling that thing the cart. There's a tension this way. There's a tension this way. There's a mass hanging times gravity this way. But the idea is the net force acting on the system equals the mass of the system times the acceleration of the system. So if I take the net force acting on the system and I divide by the mass, I get the acceleration. And then you look at that picture and then you ask yourself, what force makes that system go?
The weight.
The weight hanging. Are there any forces resisting the movement of the system?
Are we assuming the table is frictional?
Yeah, we are assuming the thing is frictionless. Then no, okay? How much mass is in my system?
0.6 kilograms.
Or generically,
Mass.
the mass of the two things added together. There you go. Done. Okay? That is the mass, that is the acceleration of this system. If the pulley is what? Massless and frictionless. same situation, but now for the pulley, which has a radius of 7 centimeters or 0.07 meters, and the pulley has a mass of 100 grams. And now we're asked to find the acceleration. So here's the question. When you put that heavy pulley into the system, are the two tensions going to be equal?
They should be, because it's one rope.
It's one rope, but are all parts of that rope doing the same thing?
They're not pulling.
Well, let me ask you this. Forget the car for a second. It's not there. Okay? Does that mass free fall?
Not with the maps.
If you just wrap the string around that pulley, does it free fall?
No.
No. Forget the air resistance. Do it in a vacuum, does it free fall?
No, because the resistance, like resistance, not just the inertia, it's not really resistance.
The pulley has inertia. Look at the problem we just worked, guys. If I cover up the car, are we back to what we just worked?
Yes.
Did it free fall?
No.
No. Is it fair to say there's effort required to turn a pulley that has weight?
Yes.
Yeah. Okay. What's the vertical portion of the string responsible for doing?
Supporting it.
Okay, yes, but in one direction you can say it supports hanging mass. In the other direction, what else does it do?
Turn the pulley.
It turns the pulley, anything else?
Pulls our cart.
And pulls the cart. The tension here has to turn the pulley and pull the cart. How about the tension here?
Just one pulley.
It just pulls the cart. Are these two tensions equal? No. These are two different tensions. And I will tell you right now, T1 is greater than T2. They're not the same when that pulley has mass. Because to say the pulley has mass is to say it's going to take effort to turn it. Yeah,
If different, two parts of the rope have different tensions, but they're still moving at the same speed.
they will still move with the same speed, yes, but the two parts have different tensions. Okay? Guys, let me just throw this problem up on the board real quick. This is your last homework problem, or something like it. Are those tensions equal?
No.
Is the tension on the right equal to the tension on the left? Okay? What's it, there's two weights here. There's the weight on the right, and there's the weight on the left.
No, well,
Which is the dominant weight?
Wait on the right.
The weight on the right. The tension on the right, what does it have to do?
it has to
Support the
pull
pulley.
the one that way, the pulley, and.
Just pull that way down.
It's not pulling the weight down.
It's pulling the
that
pulley.
way.
It causes the pulley to turn, and
Supports it.
is pulling this other thing up, right? Are these two tensions equal?
No.
What does this tension do?
Just pull up the way.
Just pull.
Just pulls up on the weight. This one's pulling up on the weight and turning that. When you have a weighted pulley, the tensions are no longer equal. Okay? So if the tensions are equal, this formula was written out, or we derived it, that's what I was looking for. We derived it based on the assumption of equal tensions. Okay? You can't use that now. Okay? So what can you do? Well, you get back to basic physics ideas. And basic physics ideas would be what? Summing forces. Okay, so if I look at this thing and I start summing forces, if I sum the forces acting on the cart, I have the tension, T2. I'm summing the forces acting on the cart in the x direction. Any other forces? What does that equal? The mass of the cart times the acceleration. I got a system with 3 different masses. We got to keep them straight. Okay? Can you solve that for anything? No. The only thing you know if there's mass. Keep going. Sum the forces for the hanging mass in the y direction. What do you see? I see T1 going up and minus the hanging weight going down. Those are the only two. What are they equal? Mass of the hanging weight times the acceleration. That's negative because it's going down. Okay? Can you solve this? No. How many unknowns are up on the board right now? 3. You don't know either tension or the acceleration. Okay? You know the masses, you know gravity. 2 equations, 3 unknowns. Okay? Gotta keep going. Is there something else I can look at? I can look at the sum of the forces after the pulley. I'll tell you that's never going to get you anywhere. But I can look at the sum of the torques acting on the pulley. If I sum the torques acting on the pulley, okay? Now I don't have the forces acting on the pulley up here yet. But the pulley is acted on by a force T1 pulling the pulley down and a force T2 pulling the pulley to the right. Remember, tensions always pull. Okay? So there's 2 torques now.
T1 minus T2.
Well, I'm going to go T. If I want to write what is the torque due to T2, it would be T2 times the radius. I need the perpendicular distance up to the force. And that distance is the radius. So T2 times R. Does T2 make the pulley want to go clockwise or counterclockwise? Clockwise. And clockwise torques are negative. T1. Okay? If I want to get the tension, the torque due to T1, it'll be T1 times the radius R, and it's counterclockwise, which makes it positive. Okay? Those are the only 2 forces trying to make this thing rotate. Anytime you sum torques, what is equal? I alpha. The sum of the torques equals I alpha. Always. Now, sometimes alpha will equal 0 if something's not moving. But here it's moving. So the sum of the torques equals I alpha. Henry, you with me, buddy? Okay. And when I wrote that alpha in there, just like the previous problem, I added another unknown. But I already have an A, and we can turn alpha into an A, can't we?
Yeah.
Because we know A equals R alpha, so I can replace alpha with A over R. So let me clean this up a little bit over here. I can factor out an R here, And I can replace I, if we're treating this pulley as a disc, what would I be?
1/2 MR squared.
1/2 mr squared. So there's my I. And now for alpha, I'm A over R. Now I got lowercase r's up here and uppercase r's over here, and I need to get a little bit more consistent. But this r takes out the square, this r takes out that r. And we're left with T1 minus T2 equals 1/2 MA. Now, if we look up here, we can see what T2 equals. T2 is simply MCA. And if we look at the next equation, we could write an expression for T1. T1 is MHG minus MHA.
Isn't it negative?
No, I bring this over to the other side of the equal sign because positive. So I get positive MHG minus MHA minus MCA for what I substituted in for T2. That's T1. That's T2. Equals 1/2. This is the mass of the disc or pulley times A. We can get A's together on one side. We get all our A's together on one side, then what can you do?
Divide by.
Well, I factor first. So MH plus MC plus 1/2 MD times A equals MHG. And now I can divide. MHG divided by MH plus MC plus 1/2 MD equals A. Whew. Now, here's the test of our answer. What happens in that formula down there if the disk is massless? The 1/2 MD does what? Goes away. And are we back to this?
Yes.
Yeah, that's a good thing. If we weren't back to that, it would be a problem. Okay? And here's what we got. Is that the force moving our system?
Yes.
How much mass is moving translationally in our system? MH, does it move translationally in a linear way? Yes. Does MC move in a linear way?
Yes.
Does MD move linearly?
No.
No. So notice, we don't get credit for all of MD moving. We get only credit for half of it's moving, and that half comes from where? The moment of inertia coefficient. Okay? So we know masses, we can plug in there, we can get an answer if we wanted to. C, for the case where the pulley has mass, find the tension in both segments of the string. Can we get that tension?
Yes.
Is that going to be hard?
Once you got it.
Not now it isn't. What am I do?
Just plug it.
Just plug in. Here's one tension in terms of A, and there's the other tension in terms of A. So find the two tensions, piece of cake. Some people will try to memorize this. Okay? Good luck to you. And even if you memorize it for the test on Monday, you're not going to remember it on the AP exam.
Wait,
Isn't it Wednesday?
Wednesday.
what do you say?
Even if you remember for the test on Wednesday, you're not going to remember for the AP exam. Okay? Guys, can you remember how to write these?
Yes. Yeah.
I hope so. Concentrate on the big ideas. They never leave you. Shortcuts are temporary. Big ideas are forever. Okay? I never will forget one time. I was teaching a staff development class to a group of teachers. And one of the new teachers in the room spoke up. It's like, Mr. Cox, so how much time do you spend preparing for your physics lectures? And Mr. Miller's over in the back corner of the room. He just puts his hand over his face. He's trying to cover his laughter. And then, and I'm trying to find a diplomatic way of saying this because she is completely overwhelmed. Because if you think you're overwhelmed as a student, imagine being a teacher teaching this class for the first time. It's a whole nother level of overwhelmed. And then I had to look this poor woman in the eyes and I thought, really none. It's like I just stumble in the room every day and grab a packet and start to, okay? And she's like, oh my God, you're a genius. I'm like, no, I'm not. I said, you know how much time it took to write this packet? I mean, there's an hour goes into each page on average. There's a lot of time and efforts put into picking the right examples. Okay? And the reason why I can walk into this, and not have done any prep is I start every problem not trying to remember a formula, because literally half the time I don't remember the end result. But I do remember the what? The big ideas, the process. Okay, and that's what you got to focus on. Also, another thing I want to point out to you. Okay? What happens if you forget that negative sign right there? Everything is thrown off. Okay? Right about this time in AP Physics, when I taught AP Physics C, I had the long, hard talk with my Physics C kids, who generally are some of the most mathematically and physically gifted kids in the building. And I said, look guys, we're getting into a section of the course where I'm going to assign you problems that, quite honestly, given time constraints, I can't expect you to get them 100% right. They are that freaking hard. We're not going to go quite there. Okay? So, how do you become successful when you're being asked to do problems that you're not even expected to get them all right? Arjuna, this is going to hurt for coming out of your mouth.
Showing as much work as possible.
Showing as much work as possible in a way that someone can understand it. Okay? It's hurting them bad. Okay? But that's what it comes down to. Okay? The last part of this problem is part D. It says, explain Arjuna, if you come out of high school starting to show work, I will consider myself a success in life. Okay? Explain the importance of the cart having lightweight wheels.
They don't have a limit of inertia.
So
So it doesn't increase the thing.
if the wheels, let's answer it by thinking the opposite. If the wheels were really, really heavy, would it matter?
Yes.
They would have a moment of inertia, so
So they isolate themselves from everything.
they would take more energy to get them going. A cart with really heavy wheels will move slower or will accelerate slower than a cart with light wheels. We're not going to do a calculation for that, but I think we're all starting to at least feel that. Okay. I'm quitting right there. You probably had enough anyway. Okay? So, we'll quit there. Some of you probably have some registration material with you today. Those you, if you want to go ahead, homework for tonight is 41 through 47, omit 46. Okay? Do these problems tonight. I'm not checking homework tomorrow. But if you show up tomorrow without having done your homework, and the assignment is for you to work on the homework is to go over the homework in groups, you are a blood-sucking leech. Because you have nothing to contribute to the group. Even if you try and don't get them, you can now enter the conversation. But if you don't try, you have nothing to contribute. Okay? So, make sure